Understanding Physics, 3 volumes in 1, by Isaac Asimov. Chapter 14. Heat. The Kinetic Theory of Gases. If the atomic theory of gas structure, made inevitable by Boyle's experiments, is to be accepted, it ought to explain the gas laws described in the previous chapter and earlier. The first man to attempt this seriously was Bernoulli, of Bernoulli's principle, in 1738. If gases are composed of separate particles, atoms or molecules, spaced widely apart, it may reasonably be assumed that these are in constant free motion. If this were not so, and the gas molecules were motionless, they would, under the force of gravity, fall to the bottom of a container and remain there. This is indeed the case for liquids and solids, where the atoms do not move freely but are in virtual contact and are constrained to remain so. The assumption that gases are made up of particles in motion, each particle virtually uninfluenced by the presence of the others, is the kinetic theory of gases. Kinetic, of course, from a Greek word meaning to move. For the moment, we will not ask why the particles should be moving, but will merely accept the fact that they are. The kinetic energy of the gas particles must far surpass the feeble gravitational force that can be exerted by the Earth on so small a particle. Remember that the force of gravity upon the particle depends in part upon the mass of the Earth multiplied by the mass of the particle. See page 44. And the latter is so small a quantity that the total force is minute. To be sure, the pull of gravity is not zero, and on a large scale it is effective. The Earth's atmosphere remains bound to the planet by gravitational force, and most of the particles of the gas surrounding our planet remain within a few miles of the surface. Only thin wisps of gas manage to make their way higher. Nevertheless, for small quantities of gas, for quantities small enough to be contained within man-made structures, the effects of gravity are minute enough to ignore. Consequently, the particles within such containers can be viewed as moving with equal ease in any direction, upward and sideways, as easily as downward. In any given container, the random motion of the particles in any direction keeps the gas evenly spread out. The even spreading of the gas within the container is enough to show that the motion must be random. If it were not, gas would accumulate in one part or another of the container. If the same quantity of gas is transferred to a larger container, the random motion of the particles will spread them out evenly within the more spacious confines. Thus a gas expands to fill its container, however large, and unless the container is so huge that the effect of gravity can no longer be ignored, fills it evenly. On the other hand, if the gaseous contents of a large container are forced into a smaller one, the particles move more closely together, and the gas can be made to fit into the smaller confine. There is none left over. If we consider the moving gas particles, however, it is clear that no individual particle can move for long without interference. One particle is bound to collide with another sooner or later, and all are bound to collide every now and then with the walls of the container. One must assume these particles have perfect elasticity and bounce without overall loss of energy. If this were not so, the particles would gradually slow and lose energy as they bounced, until finally they were brought to a state of rest or near rest, and fell to the bottom of the container under the pull of gravity. But this does not happen. If we isolate a container of gas as best we can and keep it, that container remains full of gas indefinitely. Bernoulli pointed out that the bouncing of gas particles off the wall of a container produced an effect that could be interpreted as pressure. As it bounced, each particle subjected the wall to a tiny force, and the total force over a unit area was the pressure. Strictly speaking, what we call pressure, then, is actually a great many separate pushes. There are so many of these spread so thickly through time, and each separate push is so tiny that the whole is sensed as a smooth, even pressure. Since the particles move freely and randomly in all directions, pressure is equal in all directions. Suppose that a gas is in a container topped by a frictionless piston, with just enough weights resting upon it to balance the gas pressure, the force of the particles bouncing up against the surface of the piston. If one of those weights is removed, the external force pressing down upon the upper surface of the piston is decreased. The upward force of the bouncing particles is greater than the downward force that remains, and the piston moves upward. However, as the piston moves upward, the volume of the container increases. As the volume increases, each particle of the gas has, on the average, a greater distance to travel in order to reach the underside of the piston. Naturally, then, the number of collisions against the wall in any given instance must drop off, as each particle spends more time traveling and less time colliding. The pressure decreases in consequence. Eventually, the pressure drops to the point where it is balanced by the fewer weights on the piston, and the piston rises no more. Gas volume has increased as pressure decreased, in the manner described by Boyle's law. Suppose instead that additional weights had been added to those originally present on the piston. Now the downward force of gravity moves the piston downward against the force of the particle collisions. As the piston moves downward, the volume decreases. Each particle has, on the average, a smaller distance to travel in order to reach the underside of the piston. The number of collisions, in any given instant, rises and pressure increases. Eventually, the pressure increases to the point where the additional weight on the piston is balanced. Gas volume has decreased and pressure has increased, again in the manner described by Boyle's law. A century after Bernoulli's time, when the effect of temperature on the volume and pressure of gases came to be better understood, it was necessary to expand the kinetic theory of gases in order to explain the involvement of temperature. Imagine a gas in a closed container with immovable walls. If the temperature of the gas is raised, its pressure against the walls increases. This was first observed by Amontons, see page 191, and is to be expected from the ideal gas equation, equation 13-12. For if volume times pressure is proportional to absolute temperature, and if the volume is held constant, then pressure by itself must be proportional to the absolute temperature. By kinetic theory, pressure increases only if the number of collisions of gas particles with the walls in any given instance increases. However, since the volume of the container, with its immovable walls, has not changed, the individual particles have the same distance to travel before reaching the walls, after the temperature rise, and before. To account for the fact that more of them do reach the walls, and hence raise the pressure, one must conclude that as the temperature rises, the particles move more quickly. In that case, they not only strike the wall oftener, but also more energetically. Conversely, with a fall in temperature, they move more slowly. Accepting this, let us consider a sample of gas held under a frictionless, weighted piston. The downward force of the weights is balanced by the upward force of the gas pressure. If the temperature of the gas is raised, the particles making it up move more quickly, and their collisions with the underside of the piston are more numerous and energetic. The downward force of the weights is overbalanced, and the piston is raised until the expansion of volume increases the distance that must be traveled by the particles to the point where the number of collisions is so far reduced as to be only sufficient to balance the piston once more. Thus, volume increases with rising temperature. By similar reasoning, we could argue that it would decrease with falling temperature, and thus Gay-Lussac's law is explained. I have shown how kinetic theory explains the gas laws only in a qualitative manner. In the 1860s, however, the Scottish physicist James Clerk Maxwell, 1831 to 1879, and the Austrian physicist Ludwig Boltzmann, 1844 to 1906, treated the kinetic theory with full mathematical rigor and established it firmly. We can consider some of this. Let us begin with a container in the form of a paralipid, or a brick-shaped object, in other words, with a length equal to A meters, a width of B meters, and a height of C meters. The volume, capital V, of the container is equal to A times B times C cubic meters. Suppose next that within this container are a number, n, of particles, each with a mass, lowercase n, and that all the particles are moving with a velocity of lowercase v, meters per second. These particles can be moving in any direction, but such motion can always be viewed as being made up of three components at right angles to each other. This can be done by setting up a paralipid of force, which is a three-dimensional analog of the parallelogram of force mentioned on page 40. We can arrange the mutual perpendicular components to suit ourselves, and we can select one component parallel with the length of the container, another parallel with the width, and the third parallel with the height. Since the motions are random and there is no net motion in any one direction, or the whole container would go flying off into space, it is fair to assume that each component contains an equal share of the motion. We suppose then that 1/3 of the total particle motion is parallel to the edge A, 1/3 parallel to the edge B, and 1/3 parallel to the edge C. This means that we are viewing the container of gas as containing three equal streams of particles, one moving left and right in equal amounts, one moving up and down in equal amounts, one moving back and forth in equal amounts. In reality, of course, all the particles are continually colliding with each other and bouncing and changing direction. Since the particles are perfectly elastic, this doesn't change the total motion, even though the distribution of motion among the individual particles is constantly changing. To put it as simply as possible, if one particle changes direction in one fashion, another particle changes simultaneously in such a way as to balance the first change. For this reason, we can ignore interparticle collisions. Let us focus our attention on one particle moving parallel to edge A. It strikes the face bounded by B and C head-on, and bounces back at the same speed but in the opposite direction, still parallel to edge A. So its velocity is now negative v. Its momentum before the collision was m times v, and its momentum after the collision is negative m times v. The total change in momentum is m times v minus negative m times v, or 2 times m times v. This change in momentum must be balanced by an opposite change in momentum on the part of the wall of the container if the law of conservation of momentum is to be conserved. The wall is therefore pushed in the direction opposite to the rebounding particle, and 2 times m times v represents the contribution of that one bounce of that one particle to the force on the face bounded by B and C. For the total force on the face, we need to know how many bounces there are on the entire face in a given unit of time. The single particles we have been considering, having bounced off the face, travels to the other end of the container, bounces there, comes back, and bounces off the original face a second time. It repeats the process and bounces off a third time, then a fourth time, and so on. In traveling to the other end of the container and back, it travels a distance of 2 times a meters. Since its velocity is v meters per second, the number of its collisions with the face under discussion is v divided by 2 times a times each second. The total force delivered to the wall by a single particle in 1 second is the momentum change in one bounce times the number of bounces per second. This is 2 times m times v multiplied by v divided by 2 times a, or m times v to the second power divided by a. But 1/3 of all the particles in the container, n divided by 3, are moving parallel to edge A, and each contributes the same force. The total force delivered in 1 second by all those particles is therefore n divided by 3 multiplied by m times v to the second power divided by A, or n times m times v to the second power divided by 3 times A. Pressure is the force exerted against a unit area. The wall we are considering is bounded by lines of dimensions b, meters, and c, meters. So the area of the wall is b times c square meters. To get the pressure, that is, force per square meter, one must divide the total force on the wall by the number of square meters. This means we must divide n times m times v to the second power divided by 3 times A by B times C, and we get a pressure equal to n times m times v to the second power divided by 3 times A times B times C. But A times B times C is equal to the volume, capital V, of the container. We can therefore express the pressure, P, as follows. P equals n times m times v to the second power divided by 3 times capital V equals n divided by 3 times capital V times m times v to the second power equals 2 times n divided by 3 times capital V times 1/2 times m times v to the second power. Equation 14-1. But the quantity 1/2 times m times v to the second power represents kinetic energy. See page 95. We can therefore rearrange equation 14-1 as follows. P times capital V equals 2 times n divided by 3 times 1/2 times m times v to the second power equals 2 times n divided by 3 times lowercase e followed by a very tiny little k, the symbol which represents kinetic energy. Equation 14-2. In any given quantity of gas, the number of particles is constant. Therefore, the quantity 2 times n divided by 3 is constant. Equation 14-2 tells us, therefore, that for a given sample of gas, the product of its pressure and volume is directly proportional to the kinetic energy of its constituent particles. Equation 13-12, see page 196, tells us furthermore that the product of the pressure and volume of gas is directly proportional to its absolute temperature. It is a truism that if x is directly proportional to y, and is also directly proportional to z, then y is directly proportional to z. We conclude that if P times V is directly proportional both to absolute temperature and to the kinetic energy of the gas particles, then absolute temperature is itself directly proportional to the kinetic energy of the particles of a gas, and by extension to the particles of any substance. To be sure, we have assumed that all the particles in the gas have identical velocities, and that is not so. As the particles collide with each other, momentum will be transferred in a random manner, though the total momentum will always be the same. Briefly, even if the particles had originally been moving at equal velocities, they would soon be moving over a whole range of velocities. Maxwell derived an equation that would express the distribution of particle velocities at various temperatures. If there is a distribution of velocities, there is also a distribution of kinetic energies. If we know the average velocity, however, and this can be obtained from Maxwell's equation, we know the average kinetic energy. At any temperature, there will be individual particles with very low energies, and others with very high energies. The average kinetic energy per particle, however, keeps precisely in step with the rise and fall of absolute temperature. By the kinetic theory of gases, then, we can define heat as the internal energy associated with such phenomena as the random motions of the particles, atoms, and molecules that make up matter. Absolute temperature is the measure of the average kinetic energy of the individual particles of a system. This gives an important theoretical meaning to absolute zero. It is not merely a convenience for simplifying equations, or a point at which the volumes of gases would shrink to zero if they followed Gay-Lussac's law exactly, which they do not. Rather, it is the temperature at which the kinetic energy of the particles of a substance are lowered to an irreducible minimum. Usually, this minimum is said to be zero, but that is not completely correct. Modern theories indicate that even at absolute zero, a very small amount of kinetic energy remains present. This amount, however, cannot be further reduced, and temperatures below absolute zero cannot exist. Diffusion. The motion of gas particles can also be used to explain diffusion. That is, the spontaneous ability of two gases to mix intimately, even though originally separate, and even against the pull of gravity. Suppose a container is horizontally partitioned at the center. In the upper portion of the container is hydrogen. In the lower, under equal pressure, nitrogen. If the partition is removed, it might be expected that hydrogen, by far the lighter of the two gases, would remain floating on top, as wood floats on water. Nevertheless, in a short time the two gases are intimately mixed, the nitrogen diffusing upward, the hydrogen downward, in an apparent defiance of gravity. This comes about because the motion of the gas particles is virtually independent of gravity. Again, see page 198. 1/3 of the nitrogen particles, on the average, if we assume random motion, are moving upward at any one instant, and 1/3 of the hydrogen particles are moving downward. Naturally, the two gases mix. Diffusion also takes place between mutually soluble liquids, although more slowly. For instance, alcohol can be floated on water, which is denser. If one waits, the two liquids will mix evenly. This indicates that while the particles making up liquids must remain in contact, they nevertheless have a certain freedom of movement, slipping and sliding about, so they are able to insulate themselves among the particles of another liquid. On the other hand, diffusion between different solids in contact proceeds with excessive slowness, if at all, and this is an indication that the constituent particles in solids are not only in contact, but are more or less fixed in place. This does not mean, however, that the particles of a solid are motionless. All evidence points to the fact that, although they have a fixed place, they vibrate about that fixed place with an average kinetic energy corresponding to the absolute temperature of the solid. To get a notion of the quantitative relationships that involve diffusion, let us return to equation 14-1, where P is set equal to N times M times V to the second power divided by 3 times capital V. And let us solve for V, the average velocity of the particles. This gives us the relationship V equals the square root of 3 times P times capital V divided by N times M. Equation 14-3. This is easily handled. If a given quantity of, let us say, oxygen is being dealt with, its pressure, capital P, and volume, capital V, are easily measured. The quantity, N times M, represents the number of particles multiplied by the mass of the individual particle, and that is, after all, the total mass of the gas, which is easily measured. Without going into the detail of the calculation, it turns out that at 0 degrees Celsius, or 273 degrees Kelvin, and 1 atmosphere pressure, the average velocity of the oxygen molecule is 460 meters per second, or 0.28 miles per second. Equation 14-3 can be written V equals the square root of 3 divided by N times M times the square root of P times V for a given quantity of a specific gas. N times m, the total mass is constant, so the quantity, the square root of 3 divided by n times m, is constant, and equation 14-3 can be written v equals k times the square root of p times v. And we can say that velocity of the gas molecules is proportional to the square root of pressure times volume. By equation 13-12, see page 196, however, we know that P times V is directly proportional to the absolute temperature, capital T. We can therefore say that V equals K times the square root of capital T, that the average velocity of a gas molecule is directly proportional to the square root of the absolute temperature, or that the average velocity of a gas molecule is directly proportional to the square root of the absolute temperature. If the velocity of 460 meters per second is the average for oxygen molecules at a temperature of 273 degrees Kelvin or 3 degrees Celsius, what would it be if the temperature were doubled to 546 degrees Kelvin or 273 degrees Celsius? The average velocity is then multiplied by the square root of 2, or approximately 1.4. Oxygen molecules then will move at an average velocity of 650 meters per second, or 0.40 miles per second, at the higher temperature. But suppose we consider different gases at the same pressure, capital P, and volume, capital V. Under these conditions, it turns out, as a result of evidence more appropriately considered in a book on chemistry, that the number of particles present, capital N, is the same in both. We can consider P, V, and N to be constant, therefore, and if we write equation 14-3 as V equals the square root of 3 times P times V divided by N times the square root of 1 divided by M, we can simplify this to V equals K times the square root of 1 divided by M. We are then able to say that at standard conditions of temperature and pressure, the average velocity of the molecules of a gas is proportional to the square root of 1 divided by m. Using words, we can say it is inversely proportional to the square root of the mass of individual molecules, i.e. the molecular weight. This is sometimes called Graham's law, because it was first specifically stated by the Scottish chemist Thomas Graham, 1805 to 1869, in 1829. He noted that the rate of diffusion of a gas, which turns out to depend on the velocity of its molecules, is inversely proportional to the square root of its density, and density in gases depends on molecular weight. A proper consideration of molecular weights is better taken up in a book on chemistry, but we can say that a molecule of hydrogen has a molecular weight of 1/16 that of a molecule of oxygen. Since hydrogen molecules are 16 times less massive than oxygen molecules, they move with a velocity of a square root of 16, or 4 times more rapidly. If at 273 degrees Kelvin, or 0 degrees Celsius, oxygen molecules move at 460 meters per second, 0.28 miles per second, then hydrogen molecules, at the same temperature, move at 1,840 meters per second. That is 1.12 miles per second. At 546 degrees Kelvin, or 273 degrees Celsius, the velocity of both oxygen and hydrogen molecules is multiplied by 1.4, and the latter moves at 2,600 meters per second. That is 1.58 miles per second. The velocity of sound through a gas depends in part upon the rapidity with which gas molecules can swing back and forth to form regions of compression and expansion. See page 165. As the molecules move more quickly with rising temperature, the velocity of sound does also. In different gases, furthermore, the velocity of sound is inversely proportional to the square root of the molecular weight, because that is the way molecular velocity varies. Air is 4/5 nitrogen, molecular weight 28, and 1/5 oxygen, molecular weight 32. So the average molecular weight of air is 29. The molecular weight of hydrogen is 2. At a given temperature, the hydrogen molecule moves the square root of 29 divided by 2, or 3.8 times as quickly as the average molecule in air. Since at 20 degrees Celsius, sound travels through air at the velocity of 344 meters per second, it would travel through hydrogen at that temperature at the velocity of about 1,300 meters per second. A column of air and an organ pipe, if disturbed, will vibrate at a natural frequency that depends on such things as the size of the column and the velocity of the air molecules. An organ pipe of a given size at a given temperature will therefore produce a note of a given pitch. If the pipe is filled with hydrogen, the molecules of which will move more rapidly than those of air, the same pipe at the same temperature will produce a sound of a much higher pitch. A man who fills his lungs with hydrogen, not a recommended experiment, will find himself speaking, temporarily at least, in a shrill treble. Since both the pitch of the organ pipe and the velocity of sound depend on the velocity of the molecules of a gas, one can be calculated from the other. Indeed, in about 1800, the German physicist Ernest F. Kaldny, 1756 to 1827, sometimes called the father of acoustics, calculated the velocity of sound in various gases, something rather difficult to measure directly, by noting the pitch of organ pipes filled with the gas, something quite easy to do. To be sure, the actual velocities of individual molecules cover a broad range, and some molecules of a particular gas move very rapidly. Even at 0 degrees Celsius, there would be a very small fraction of the molecules in oxygen gas moving, at least temporarily, at velocities of 7 miles per second, which is some 2.5 times the average velocity. It so happens that 7 miles per second is the escape velocity on the Earth's surface. See page 63. And a molecule moving this quickly would be expected to leave the Earth permanently. For this reason, it might seem that oxygen should constantly be leaking out of the atmosphere. So it is, but this should be no cause for panic. For one thing, there are very few oxygen molecules that can travel at 25 times the average velocity. Of those that do, all but a vanishingly small number strike other molecules and lose the unusually high velocity, long before they can reach the upper regions of the atmosphere. Such leakage of oxygen as takes place then is so slow as to assure the Earth its oxygen supply for billions of years to come. In the case of hydrogen molecules, however, with 4 times the average velocity of oxygen molecules, a larger fraction can be expected to attain the escape velocity of 7 miles per second, since this is only about 6 times the average velocity of the hydrogen molecule. Here the leakage is indeed serious, and the Earth cannot hold hydrogen in its atmosphere over the geological eras, nor has it. There is good reason to think that the Earth's atmosphere might have been rich in hydrogen to begin with, but it is all gone now. The Moon, with its much smaller escape velocity, see page 63, could not even hold any oxygen or nitrogen, if it had ever had any. In fact, it lacks an atmosphere altogether. Jupiter and the other planets, with larger velocities of escape, and with temperatures lower than those of the Earth and the Moon, can hold even hydrogen easily. The outer planets, therefore, have large hydrogen-filled atmospheres. Real gases. Boyle's law has always been accepted as useful through the 3 centuries during which scientists have been aware of its existence. Through the first 2 of those centuries, it was also wrongly considered exact. That Boyle's law, while useful, is only an approximation of the actual situation was first made clear by the French physicist Henri Victor Renan, 1810 to 1878, who in the 1850s measured the exact volumes of different gases under different pressures and found that the product of the two, P times V, was not quite constant after all, even if the temperature were kept carefully constant. Under a pressure of 1,000 atmospheres, the product could be twice as high as at 1 atmosphere of pressure, even when he worked with pressures that were only moderately high. He frequently found deviations of up to 5%. Furthermore, there were differences from gas to gas. Up to a pressure of 100 atmospheres, hydrogen, nitrogen, and oxygen deviated comparatively little from Boyle's law, while carbon dioxide deviated a good deal. Yet Boyle's law can be derived from the kinetic theory of gases. Is the kinetic theory wrong, then? No, not necessarily. However, in deriving Boyle's law from the kinetic theory of gases, it simplifies matters to make two assumptions that are not exactly true for real gases. For instance, it can be assumed that there are no attractive forces among the molecules of a gas, so the motion of one molecule can be considered completely without reference to the others. This is almost correct, but not quite, for there are very weak attractive forces among the molecules of gases. Another assumption is that the molecules are extremely small compared to the empty space separating them, so extremely small that their volume can be taken to be zero. Again, this is almost correct, but not quite. The volume of the molecules is indeed very small, but it is not zero. Now suppose we don't accept the simplifications, but consider instead that when a molecule is about to strike the wall of a vessel, there is a net pull backward from all the feeble intermolecular forces exerted upon the about-to-collide molecule by the other molecules. This is a kind of gaseous surface tension, like the more familiar liquid surface tension described on page 126. Because of this backward pull, the molecule does not strike the surface with full force, and its contribution to the pressure is less than one would expect from kinetic theory if no intermolecular forces existed. To bring the pressure of the individual molecule up to the no intermolecular force ideal, we must add a small extra quantity of pressure, or px. The ideal pressure, or pi, is then the actual measured pressure plus this extra quantity, or p plus px. The more molecules present in the gas close to the colliding molecule, the more distant molecules contribute so little to the attractive force that they can be ignored, the greater the backward pull. The more the actual pressure, P, falls short of the ideal pressure, Pi, the greater the value, Px, we must add to P in the case of this one colliding molecule. The quantity of nearby molecules is proportional to the density of the gas, d. But pressure depends upon the total number of molecules striking the walls in a given time. The value for Px also depends on that number, but that number in turn depends upon the density of the gas. Thus, Px depends on the density of the gas first in connection with each per colliding molecule, then in connection with the number of colliding molecules per unit time. The total value of Px depends upon its size per colliding molecule multiplied by the number of colliding molecules per unit time, or upon a factor proportional to density multiplied by another factor proportional to density. The total value is then proportional to the square of the density, or d to the second power. If on this occasion we use a for the proportionality constant, we can say that Px equals a times d to the second power. For a given quantity of gas, density is inversely proportional to volume. The denser a gas, the less volume is taken up by a given quantity. If Px is directly proportional to the square of the density, then it must be inversely proportional to the square of the volume. That is, px equals A divided by V to the second power. Since earlier I said that the ideal pressure was P plus Px, we can now write that as P plus A divided by V to the second power. Next, what about the matter of the finite volume of the molecules? If more and more pressure is put upon a gas, Boyle's law requires that the volume decrease steadily and get closer and closer to zero. The ideal volume, VI, available for contraction, is, if Boyle's law held perfectly, equal to all the volume, that is V, of the gas. But if a gas is actually put under great pressure, the molecules eventually make virtual contact. After all, there is practically no further shrinkage of volume with increase of pressure. The ideal volume available for contraction is the volume of the gas minus the volume of the molecules themselves. In other words, Vi equals V minus lowercase b, where lowercase b represents the volume of the molecules. The ideal gas equation, equation 13-12, see page 196, based on the assumption of no intermolecular forces and no molecular volume, should really be expressed in terms of ideal pressure and ideal volume. Pi times Vi equals R times T. If the expressions containing the actual pressure and volume are used for the ideal values, we get P plus A divided by V to the second power times V minus lowercase b equals R times T. Equation 14-4. This is the van der Waals equation, since it was first worked out by the Dutch physicist Johannes Diederik van der Waals, 1837 to 1923. In 1873, the feeble attractive forces between gas molecules that help make this modification necessary are called van der Waals forces. The values for lowercase a and lowercase b in the van der Waals equation are usually quite small and differ from gas to gas, for the various gas molecules have their own characteristic volumes and exert forces of characteristic size among themselves. The intermolecular forces in gas, while small under ordinary conditions, can be made to bring about important changes in gaseous properties. The attractive force among gas molecules increases as the molecules approach one another, and the molecules approach more and more closely as the volume of a given quantity of gas decreases with increasing pressure. Where the attractive force is comparatively large to begin with, increased pressure can raise the force to a level higher than that which can be overcome by the kinetic energy of the gas molecules. The molecules will no longer be able to pull apart, but will cling together, and this substance will become a liquid. Gases such as sulfur dioxide, ammonia, chlorine, and carbon dioxide can in this way be liquefied by pressure alone, and at this high pressure be maintained as liquids at room temperature. If there were no intermolecular forces, liquefaction could not take place under any circumstances. All substances would be gaseous under all conditions. Where the intermolecular attractive force is particularly weak, however, it is possible that even when the gas molecules are forced close enough together to touch, the attractive force will still not have increased to the point where it can keep the molecules together against the molecular motion representing their kinetic energy. For that reason, gases such as oxygen, nitrogen, hydrogen, helium, neon, or carbon monoxide cannot be liquefied at room temperature under any pressure, no matter how high. During the early 19th century, gases of this sort therefore received the name of permanent gases. However, one might increase the attractive force and decrease the kinetic energy as well. If the former is brought about by increasing the pressure, the latter can be brought about by decreasing the temperature. If the temperature is brought low enough, the kinetic energy is decreased sufficiently for the attractive forces among the molecules of the so-called permanent gases to suffice to bring about liquefaction. The temperature at which such liquefaction becomes just barely possible is called the critical temperature. Above that critical temperature, a substance can exist only as a gas. The existence of the critical temperature was first discovered by the Irish physicist Thomas Andrews, 1813 to 1885, in 1869. The critical temperature for oxygen is 154 degrees Kelvin, or negative 119 degrees Celsius, and it was only after oxygen was brought to a lower temperature that it became possible to liquefy it. Hydrogen, with still weaker intermolecular forces, must be lowered to a temperature of 33 degrees Kelvin, or negative 240 degrees Celsius, before the kinetic energy of the molecules is low enough to be neutralized by those forces. The record in this respect is held by helium, not isolated on Earth until 1898. Helium is the nearest approach among real gases to the gaseous ideal. Its critical temperature is 5 degrees Kelvin, or negative 268 degrees Celsius. On the other hand, there are substances with intermolecular forces so great that they remain liquid at room temperature even under atmospheric pressure. These intermolecular forces are more than mere van der Waals forces, and they will not be discussed in this book. Water is the most common example of a substance liquid at ordinary temperatures and pressures. At a temperature of 373 degrees Kelvin, or 100 degrees Celsius, and 1 atmosphere pressure, the intermolecular forces are overcome, thanks to the heightened kinetic energy, and water turns into its gaseous form, steam, or water vapor. At temperatures over 100 degrees Celsius, water can be kept in liquid form by increasing the pressure. This means that the boiling point rises with increased pressure, a fact taken advantage of in pressure cookers. The critical temperature for water is 647 degrees Kelvin, or 374 degrees Celsius, and it is only at temperatures above that liquid water cannot exist under any conditions. Even in liquids, the attractive forces between molecules are not large enough to prevent the individual molecules from slipping and sliding about. If, however, the temperature is lowered still further, a point is reached where the energies of the individual molecules are insufficiently large to give it even that much freedom. The intermolecular forces are strong enough to keep the molecules firmly in place. They may vibrate back and forth, but the average position remains fixed, and the substance is a solid. If the temperature of a solid is raised, the vibrations become more energetic, and at a certain temperature, depending on the size of the intermolecular forces involved, they become large enough to counter those forces to the extent of allowing the molecules to slide about. The solid has then melted, or liquefied. The melting point is only slightly affected by pressure. The intermolecular forces of hydrogen are so weak that solid hydrogen melts at a temperature of only 14 degrees Kelvin, or negative 259 degrees Celsius, and liquid hydrogen boils under atmospheric pressure at a temperature of only 20 degrees Kelvin, or negative 253 degrees Celsius. Helium does better still. Its particles consist of individual atoms, and the interatomic forces are so weak that even the irreducible bit of kinetic energy still present at absolute zero is enough to keep it liquid. Solid helium cannot exist at any temperature, however low, except under pressures greater than atmospheric. The boiling point of helium under a pressure of 1 atmosphere is 4 degrees Kelvin, or negative 269 degrees Celsius. On the other hand, some substances possess intermolecular or interatomic forces so strong that they remain solids at ordinary temperatures and even considerably higher. The metal tungsten does not melt until a temperature of 3,370 degrees Celsius is reached, and does not boil under atmospheric pressure until a temperature of 5,900 degrees Celsius is reached. Specific heat. So far in our discussion of heat in this chapter and the preceding one, the emphasis has been on temperature, and we must avoid confusing the two. The terms heat and temperature are by no means identical. It is all too easy to assume that if one sample of water has a higher temperature than another, it is hotter and therefore has more heat. The final conclusion, however, is not necessarily true. A thimble of water at 90 degrees Celsius is much hotter than a bathtub full of water at 50 degrees Celsius. But there is more total heat in the bathtub of water. If both are allowed to stand, the thimble full of water will have cooled to room temperature in an interval during which the bathtub full of water would scarcely have cooled at all. The thimbleful loses its heat more quickly because, for one thing, it has far less heat, all told, to lose. To specify, the heat content of a system is the total internal energy of the molecules making it up, while the temperature is the measure of the average translational kinetic energy of the individual molecules. In other words, heat represents a total quantity, and temperature a quantity per molecule. The difference can be made plainer, perhaps, by an analogy. Consider 1 liter of water poured into a tall, thin cylinder, so that it forms a column 1 meter high. Into a much broader cylinder, 5 liters of water are poured, and this water stands only 0.1 meters high. The water in the narrow cylinder exerts the greater pressure on the bottom of the container, but the water in the broader cylinder, exerting 1/10 the pressure, is nevertheless 5 times greater in volume. Volume is a total quantity, while pressure is a quantity per area. Therefore, temperature is to heat as pressure is to volume. It may seem that such a distinction between heat and temperature is unnecessary labor. After all, if one heats water, for instance, heat pours into it, and the temperature goes up. The two rise together, and why can't you use one as the measure of the other? Unfortunately, this parallel behavior of heat and temperature can be counted on only when you deal with a given quantity of a particular substance, and even then, only over certain limited temperature ranges. We can see this if we compare the heat contents of 2 different subjects at identical temperatures. To do this, we need a unit of measurement for heat. Earlier in the book, I mentioned such a unit, the calorie, in passing. Now let's go into such matters in a bit more detail. Suppose we add heat to water, thus rising its temperature. Experiments will show that the amount of heat required to raise the temperature of water by a fixed number of degrees varies with the mass of the water receiving the heat. We can assume, for instance, that 100 grams of boiling water contains a fixed amount of heat. If 100 grams of boiling water are poured into 5 kilograms, 5,000 grams, of cold water, the temperature of the cold water will rise about 2 Celsius degrees. If, on the other hand, the 100 grams of boiling water is poured into 10 kilograms of cold water, the temperature of the cold water will go up only 1 Celsius degree. Again, the quantity of heat required to raise the temperature of a fixed mass of water varies with the number of Celsius degrees by which the temperature is raised. It takes twice as large a volume of boiling water to raise a particular quantity of cold water by 10 Celsius degrees, then by 5 Celsius degrees. The unit of heat must therefore be defined in terms of a unit mass and a unit rise in temperature, as for instance the quantity of heat required to raise the temperature of 1 gram of water by 1 Celsius degree. Actually, refined measurements show that the quantity of heat required to raise the temperature of 1 gram of water by 1 Celsius degree varies slightly according to the original temperature of the water, so the original temperature must also be included in the definition. We can say then, 1 calorie is the quantity of heat required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. We might also say that 1,000 calories, or a kilocalorie, is the quantity of heat required to raise the temperature of a kilogram, 1,000 grams, of water from 14.5 degrees Celsius to 15.5 degrees Celsius. Suppose now that a gram of aluminum is placed in boiling water for enough time to make certain that it has assumed the temperature of boiling water, that is 100 degrees Celsius. Plunge the hot aluminum quickly into 100 grams of water at 0 degrees Celsius. The aluminum cools off and its heat is added to the water, raising its temperature from 0 degrees Celsius to about 0.22 degrees Celsius. To raise the temperature of 100 grams of water by 0.22 Celsius degrees takes 100 times 0.22, or about 22 calories. The gram of aluminum, in cooling from 100 degrees Celsius to 0.22 degrees Celsius, has liberated some 22 calories. By the law of conservation of energy, we would expect that if this cooling liberated 22 calories, then adding 22 calories to the cold aluminum would bring it back to 100 degrees Celsius. Roughly speaking, then, we can say that it takes 22 calories to raise the temperature of a gram of aluminum 100 Celsius degrees, and 0.22 calories to raise it 1 Celsius degree. This represents the specific heat of aluminum, where the specific heat of a substance is defined as the quantity of heat required to raise the temperature of 1 gram of that substance by 1 Celsius degree. By this type of experiment, one can find that the specific heat of iron is 0.11, that of copper 0.093, that of silver 0.056, and that of lead 0.03. If 1 calorie of heat is added to a gram of aluminum at 0 degrees Celsius, that amount of heat will be enough to heat it. 1 divided by 0.22, or 4.5 Celsius degrees. That is, to a temperature of 4.5 degrees Celsius. The same amount of heat under the same conditions would raise the temperature of a gram of iron to 9 degrees Celsius, of copper to 11 degrees Celsius, of silver to 18 degrees Celsius, and of lead to 33 degrees Celsius. Here you can see that the distinction between heat and temperature is indeed a useful one, since the same quantity of heat may be added to a fixed mass of each of a number of different substances, and each will attain a different temperature. Temperature in itself is consequently no measure at all of total heat content. To return to our volume pressure analogy, this is like pouring equal volumes of water into cylindrical vessels of different diameters. The volumes may be the same, however the final pressures will vary. The pressure is no measure at all of total volume. The conception of specific heat was first advanced by the Scottish chemist Joseph Black, 1728 to 1799, in 1760. Part of the reason for this variation of specific heat from substance to substance lies in the different masses of the atoms making up each. The lead atom is about 7.7 times the mass of the aluminum atom. The silver atom is 4 times the mass of the aluminum atom. The copper atom is 2.3 times the mass of the aluminum atom, and the iron atom 2.1 times the mass of the aluminum atom. Because of this, a given mass of lead, say 1 gram, contains only 1 divided by 7.7 times as many atoms as the same mass of aluminum. In adding heat to 1 gram of lead, you are therefore engaged in setting fewer atoms into motion, and less heat is required to increase the kinetic energy of the individual atoms by enough to account for a 1 Celsius degree temperature rise. For this reason, the specific heat of lead, 0.03, is about 1 divided by 7.7. That of aluminum, 0.22. Similarly, the specific heat of silver is about 1/4 that of aluminum. The specific heat of copper is about 2.3, and the specific heat of iron is about 2.1 that of aluminum. The general rule is that for most elements, the specific heat multiplied by the relative mass of its atoms yields a number that is approximately the same for all. Where the relative mass of the atoms of the different elements, the atomic weight, is chosen in such a way that the hydrogen atom, which is the lightest, has a weight of a trifle over 1. Then the product of specific heat and atomic weight comes to about 6 calories for most elements. This is known as the law of Dulong and Petit, after the French physicist Pierre-Louis Dulong, 1785 to 1838, and Alexis Thérése Petit, 1791 to 1820, who first advanced it in 1819. Latent heat. It might occur to you that temperature is very close to being a measure of heat content, if only we count by atoms or molecules, instead of by grams. This would be so if the law of Dulong and Petit held for all substances under all conditions, but it does not. It holds only for the solid elements, and for those only in certain temperature ranges. In fact, it is possible to show cases in which heat content can change a great deal without any change in temperature at all, and that should at once put to rest any notion of using temperature as a measure of heat content. Suppose 100 grams of liquid water at 0 degrees Celsius is added to 100 grams of liquid water at 100 degrees Celsius. After stirring, the final temperature of the mixture would be 50 degrees Celsius. Next, suppose that 100 grams of ice at 0 degrees Celsius is added to 100 grams of liquid water at 100 degrees Celsius. After allowing the ice to melt and stirring the mixture, assuming that while we wait, there is no overall loss of heat to the outside world or gain of heat from it, a matter which can be arranged by insulating the system, we find that the temperature of the mixture is only 10 degrees Celsius. Why should this be? Clearly the liquid water at 0 degrees Celsius had more heat to contribute to the final mixture than the ice at 0 degrees Celsius, and yet both liquid water and ice were at the same temperature. It seems reasonable to suppose that a quantity of the heat in the hot water was consumed in the second case, in simply melting the ice. So much the less was therefore available for raising the temperature of the mixture. Indeed, if we heat a mixture of ice and water, we find that no matter how much heat is transferred to the mixture, the temperature remains at 0 degrees Celsius until the last of the ice is melted. Only after all the ice is melted is heat converted into kinetic energy, and only then can the temperature of the water begin to rise. Experiment shows that 80 calories of heat must be absorbed from the outside world in order that 1 gram of ice might be melted, and that no temperature rise takes place in the process. The ice at 0 degrees Celsius is converted to water at 0 degrees Celsius. But if the heat gained by the ice is not converted into molecular kinetic energy, what does happen to it? If the law of conservation of energy is valid, we know it cannot simply disappear. The water molecules in ice are bound together by strong attractive forces that keep the substance a rigid solid. In order to convert the ice to liquid water, in which the molecules, as in all liquids, are free of mutual bonds to the extent of being able to slip and slide over, under, and beside each other, those forces must be countered. As the ice melts, the energy of heat is consumed in countering those intermolecular forces. The water molecules contain more energy than the ice molecules at the same temperature, not in the form of a more rapid motion or vibration, but in the form of an ability to resist the attractive forces tending to pull them rigidly together. The law of conservation of energy requires that the energy change in freezing be the reverse of the energy change in melting. If liquid water at 0 degrees is allowed to lose heat to the outside world, the capacity to resist the attractive forces is lost, little by little. More and more of the molecules lock rigidly into place, and the water freezes. The amount of heat lost to the outside world in this process of freezing is 80 calories for each gram of ice formed. In short, 1 gram of ice at 0 degrees Celsius, absorbing 80 calories, melts to 1 gram of water at 0 degrees Celsius, and 1 gram of water at 0 degrees Celsius, giving off 80 calories, freezes to 1 gram of ice at 0 degrees Celsius. The heat consumed in melting ice, or any solid for that matter, is converted into a sort of potential energy of molecules. Just as a rock at the top of a cliff has, by virtue of its position with respect to gravitational attraction, more energy than a similar rock at the bottom of the cliff, so do freely moving molecules in liquids, by virtue of their position with respect to intermolecular attraction, possess more energy than similar molecules bound rigidly in solids. It is the kinetic and potential energies of the molecules that together make up the internal energy that represents the heat content. It is the kinetic energy only that is measured by the temperature. By changing the potential energy only, as in melting or freezing, the total heat content is changed without changing the temperature. The discoverer of the fact that heat melted ice without raising its temperature was Joseph Black, who first pointed out the significance of specific heat. See page 215. He referred to the heat consumed in melting as latent heat. Latent refers to something that is present in essence, but not in such a fashion as to be apparent or visible. This is just about synonymous with potential, so the connection between latent heat and potential energy is clear. Actually, the heat required to melt a gram of ice is its latent heat of fusion, fusion being synonymous with melting. The qualifying phrase of fusion is necessary for another type of latent heat arises in connection with boiling or vaporization. In converting a gram of liquid water at 100 degrees Celsius to a gram of steam at 100 degrees Celsius, what remains of the intermolecular attractions must be completely neutralized. Only then are the molecules capable of displaying the typical properties of gases, that is, the virtually independent motion. In the earlier process of melting, only a minor portion of the intermolecular attractive force was countered, and the major portion remains to be dealt with. For this reason, the latent heat of vaporization of a particular substance is generally considerably higher than the latent heat of fusion for that same substance. Thus, the latent heat of vaporization of water, the amount of heat required to convert 1 gram of water at 100 degrees Celsius to 1 gram of steam at 100 degrees Celsius, is 539 calories. For water, the latent heat of vaporization is almost 7 times as high as the latent heat of fusion. The energy content of steam is thus surprisingly high. 100 grams of water at 100 degrees Celsius can be made to yield 10,000 calories as it cools to the freezing point. 100 grams of steam at 100 degrees Celsius, however, can be made to give up 53,900 calories merely by condensing it to water. The water produced can then give up another 10,000 calories if it is cooled to the freezing point. It is for this reason that steam engines are so useful, and a hot water engine would never do as a substitute. It is also no accident that James Watt, the perfecter of the steam engine, was a student of Joseph Black. The latent heat of vaporization can be put to an important use. Suppose that a gas, such as ammonia, is placed under pressure in a closed container. If the pressure is made high enough, it will liquefy the gas. See page 210. As the ammonia liquefies, it gives up a certain amount of heat to the outside world. This heat would tend to raise the temperature of the immediate surroundings and of the ammonia itself. However, if the container of ammonia is immersed in running water, the heat evolved is carried off by that water, and the liquid ammonia is no warmer than the gas had been. If the container of ammonia is now removed from the water, and the pressure is lowered so that the liquid ammonia is free to boil again and become a gas, it must absorb an amount of heat equivalent to what it had given up before. It absorbs this heat from the nearest source, itself, and its immediate neighbors. Some of the kinetic energy of its own molecules is converted into the potential energy of the gaseous state, and the temperature of the ammonia drops precipitously. If a gas like ammonia is made part of a mechanical device that alternately compresses it and allows it to evaporate, a heat pump will have been set up, in which heat is pumped from the ammonia and anything in its neighborhood out by way of running water, for instance, to the world at large. If such a heat pump is placed within an insulated box, we have a refrigerator. The lowering of temperature with vaporization is made use of by our own bodies. The activity of the sweat glands keeps us covered with a thin film of moisture which, as it evaporates, withdraws heat from our body and keeps us cool. Water has the highest latent heat of vaporization of any common substance, so the fact that our perspiration is almost pure water means that little of it need be used, and we are ordinarily unaware of it. In hot weather, the process must be accelerated, and if humid conditions cut down the rate of evaporation, perspiration will accumulate in visible quantities. We all know the feeling of discomfort that follows upon this partial breakdown of our own private refrigeration device.